Log on, tune in, find out. Another good idea from Cambridge.
The speaker is Dmitriy Rumynin, and he will speak about double cells and representations.
Hello. Double cells, Kazhdan-Lusztig cells, have been with us for over a quarter of a century. I think Lusztig introduced them in 80s, but so far they resisted any attempts to penetrate them by our intelligence, and we still know very little about them except affine case. And nowadays it's fashionable to study cells with two parameters, but my talk will be about cells with one parameter, and there will be three parts. I'll first discuss about cells, then I'll discuss base sets, and then I'll talk about representations. And there will be more questions than answers in my talk. And if you know any answers to any questions I pose, I would be very welcome to know. So it would be very nice to know. Let's start. Let's start with the bigger generality. We take a Coxeter group W, which has finitely many generators and which is connected, and it comes with various Kazhdan-Lusztig stuff. There are Kazhdan-Lusztig equivalences left, right, and two-sided, and Kazhdan-Lusztig preorders left, right, and two-sided. And preorder means it's not quite an order. It means if you take a quotient by this equivalence, then it will be a proper order on the quotient set. So here are 5 questions I've just thought for this talk, which seems to be quite elementary about these structures, and all of them are known in affine for affine Weyl groups, but I don't know, well, but in general they seem to be very, very hard. So here are 5 questions, and let me go over them. First of all, this is cells are equivalence classes, left cells of this equivalence, right cells of this equivalence, two-sided cells of this equivalence. Is this set of double cells finite? Well, I don't know any counterexamples. Now, if you take this set and consider this as a partially ordered set, does it have a unique maximal element? Well, again, we know in a affine case there is a big cell. This is an interesting question. It says that if two elements sit in the same two-sided cell, and the left cell of one of them is finite, is the left cell of the other finite? And for affine ones, it follows from Bezrukavnikov-Ostrich result. And in general, again, I don't know. Number 4 is, if you take a simple reflection, they all sit in the same two-sided cell. So for some of Coxeter groups, it's finite. For some, it's infinite. Can you give is it possible to give a complete classification? Well, again, for a affine case, we know that essentially the infinite ones are type A, type B2, and type Cn, and the rest of them are finite. And finally, is this equivalence relation decidable? And there is a stronger question asked by Kasselman in '94. Essentially, the conjecture of Kasselman was that if you take minimal expressions of all the elements of the cell, that they form a regular language. And it somehow means that it will be decidable, but even on a finite automata. For affine cases, for affine Weyl groups, this is mostly known thanks to the work of Xi. And but formally it has been written down by Gunnels recently. The one thing annoying about question 5 is that we expect that this left relation is decidable, but one still can't do it on a computer. So there is, if you want to ask your computer, well, if you're using any standard packages and you want to ask whether two elements are in the same left cell, you are out of luck. You won't be able to do it except for maybe finite Coxeter groups. There is obviously, there is Paul Gunnels who can do it with a limited efficiency. So, but I don't know what he's doing. But he has some programs. Well, these programs are not publicly available, which can answer whether this is decidable. Well, let's look at the pictures first. So the cells are nice because you can draw them. So these are two Coxeter groups. This one, 3, 7, and this is a classical picture. It has been, so cells here have been computed by Lustig in the 80s. This has been computed by Paul Gunnels. So what that is, so this is a tessellation of affine space, and this is a tessellation of hyperbolic plane, and each triangle corresponds to an element of the Weyl group, or of the Coxeter group. And you can see that simple, well, this is identity element, and these are simple reflections. So this group acts on the plane here, and this group acts on the plane here, and this is a fundamental domain. In particular, you can see the difference between these two pictures is in the angles of these two triangles. So here is 90 degrees, and here is 60 degrees, and here it's 30 degrees, and here it's pi over 7. So that's why there is 7 here. And the double cells are regions which are colored by the same color. And the left cells are connected regions colored by the same color. So you can see these pictures are quite similar in a sense. Any questions? The next thing I'd like to do is just to recall a definition of a left cell, so that people who don't remember will see what the definition is and what the difficulty is. And there are various definitions, and I'm using the most computational one. Somehow, if you want to compute the cells, especially if you want to compute it on a computer, that's what you have to do. Well, let me open the whole definition so that you enjoy its full beauty. Essentially, you have to use on W, there is usual Brouillard, or the usual length in generators of S and Kazhdan-Lustig polynomials. And then there is this thing called mu relation. And we say that X and Y are in mu relation. If X is less or equal than, well, there are two cases, right? X could be less or equal than Y, and the degree of Kazhdan-Lustig polynomial should be as big as possible. Can't go over this. Or alternatively, X could be greater than Y, and the degree of Kazhdan-Lustig polynomial in the opposite order has to be maximal. Then we need descent sets, And this is very easy. These are all simple reflections which increase an element, which decrease the element if you multiply on the left. That's why it's called left descent set. And then one can define Kazhdan-Lusztig preorder. And x or less or equal than y in Kazhdan-Lusztig preorder, you can only if there exists a chain of mu relations going from x to y, such that for every k in this chain, we have this non-containment of descent sets. And the rest of it is actually quite easy. Then you say that x is equivalent to y if x is less or equal than y and y is less or equal than x. And the right one could be, well, the right one is left equivalence on the inverses, and two-sided one is some kind of joint, so equivalence relation between left and right. So it's quite involved, but but there are two inherent difficulties in this definition. If you try to program it, the first difficulty you are going to hit here, because although Kazhdan-Lusztig polynomials are computable, their computation is very, very computationally intense. So there is a high complexity involved here. And the second thing is hidden here, the second difficulty, in finding your mu relations. So for instance, you have two elements x and y, and they have some, say, length 100, right? So x has a length 100, y has a length 100. You want to know how to go from, well, how to find mu relations. The difficulty is, a priori, we don't know any bound on the length of the mu relation, of this chain of mu relations involved. So you may start with elements of length 100, but to construct them, so typically, some of the elements, well, elements here may start increasing their length. So somewhere here you may have an element of length, say 500 or 600, and you don't know where to stop. So you don't know up to which length you have to write your mu relations, and that's why it's not immediately clear whether it's computable. That's it. Any questions at this point? Right. And, well, I'm going to base sets. And now I'm going to concentrate on affine case. So the Coxeter groups, which we can understand, well, there are several classes which probably we can understand. So we can understand finite ones, we can understand affine Weyl groups. There is some hope of understanding of crystallographic, because they are Weyl groups of Katz-Moody groups, of Katz-Moody Lie algebras. Then there is a case of hyperbolic, and I think Paul Gunnels and Misha Belalipitsky are trying to prove this Hassel's conjecture for hyperbolic ones, but there I don't understand. Well, probably they're both hyperbolic geometers, so I think hyperbolic means you should be able to understand, but they haven't proved it yet.
There was a conjecture that the left cells are connected in the Coxeter complex. Is that known?
For affine ones. In general, no.
In general?
I think, no. In general, it's not known. But on the picture, you can see, yes, there was this conjecture.
Is it known to be, it's not known?
I think I wouldn't bet anything on that, but I think for affine ones it's known, but in general it's not. And then it's known for some funny cases, like maybe right angled or something. Okay, but before I have to tell you what a set is. And, well, if you know what a set is, maybe you have to, well, let's start again. What is a set? Well, we have a finite group G, and a set, we are interested in a finite set with an action of G is not just, well, that's the definition of what a set is. That's my definition of a set. Well, it's called extended, so that you remember that it's not just a set. So it's a G-Marita equivalence class of a finite dimensional semi-simple associative G algebra over C. What it means is, well, Marita equivalence means there is a Marita context between these algebras, so this finite group acts on this algebra A, and G-Marita equivalence means that all modules in all the bimodules in the Marita context have to be G modules, and all the maps in the Marita context have to be maps of G modules. Yes, so this is my definition of a set. Why? Well, let me just open the rest of transparencies. Why is it a set? First of all, because I can think of this as a set. Given such a Marita equivalence class of an algebras, I can consider the set of its simple modules or irreducible representations, and this is a G set. So it's some set with some additional structure. If I have sets, I want to take the disjoint union. And the disjoint union will be a Marita equivalence class of the direct sum. And I want to take a direct product of sets, and the direct product of sets will be a Marita equivalence class of a tensor product. And then I teach my algebra students that there is beautiful orbit stabilizer theorem, and there is orbit stabilizer theorem for these extended sets as well. So every set will be a disjoint union of quotient sets, but they're not, well, there is this little alpha I, and what are these quotient sets with this little alpha I? So IHI is a subgroup of G, and alpha I is some element in a Schur multiplier of HI. So it's a second co-cycle. And what is this set? I pick some representation of HI, but it's not irreducible one, but it's not linear, it's projective with this element alpha I, with, so it's Q with respect to alpha I. And I take a direct sum of endomorphism algebras of V, of just linear map, parametrized by the quotient set. So there is a natural action of G on this algebra, and this is my quotient, extended quotient set. There are other things you can do. There is a Burnside ring, extended Burnside ring of these sets, which is very useful for calculating, but I'm not going to talk about extended Burnside ring. But I need some Euler characteristic of this set, right? But I don't need usual Euler characteristic. I need G-equivariant Euler characteristic. So what is a G-equivariant Euler characteristic of a point? So if you have a group G, which acts on a point, then the Euler characteristic should be the size of a G-equivariant K-series. So on a point, well, there are, for each representation of G, you have a vector bundle of a point. So somehow Euler characteristic of a point should be the number of representations of G. And here I do essentially the same. So I have to observe that if two algebras are G-Marita equivalent, then the skew group algebras are G-Marita equivalent. And the equivariant Euler characteristic of my set is just the number of irreducible modules of this of a skew group algebra. And it's well defined because, well, if these two give me the same G-Marita equivalence class, that these two are Marita equivalent, these numbers are the same. And somehow this category is quite important. So Bezrukavnikov and Ostrich are thinking about it as a coherent sheaves on an extended G set. Any questions at this point? Now, why I'm telling you all about this extended G sets? Because there is Robinson, Schoenstatt, Lustig, Bezrukavnikov, Ostrich correspondence. Well, I don't think anyone calls it that way, but there is a reason. There is Robinson-Schoenstatt correspondence, which predates cells, and in modern language, it essentially for a symmetric group, it computes left and right cells. Then, for fine Weyl groups, Lustig made a conjecture in the 80s that these base sets exist, and it was proved by Bezrukavnikov and Ostrich in 2004. And the way I'm going to formulate it in terms of correspondence. Let me show you the rest of the slide. So as I say, I'm interested in affine Weyl groups. Then, that's a theorem by Bezrukavnikov and Ostrich, which was conjectured by Lustig before. So essentially, for each double cell, there exists a reductive group. So this is a connected reductive group. This is a finite group. It's a semi-direct product. And an extended AC set, let me call it XC, and it's a Morita equivalence class of an algebra BC, and the bijection. So on one hand, the bijection goes between W, and on the other hand, it's a union of all cells of irreducible representation. Well, you have to think, well, I have to say maybe a couple of words what that is. So this is a finite dimensional algebra. That's another finite dimensional algebra on which GC acts. But this is an infinite group. So you want still the representations of this. So it's a reducible representation of this infinite dimensional algebra, which restricted to group are rational. So you can try to think of this in terms of certain data, and the way to write it, you can think of these irreducible representations as coherent sheaves on this finite set, which are equivalent with respect to GC, and each representation can be written using the following data. You essentially need a point AB in BC, and then you need a stabilizer of a point and its representation, and then using this local data, a point and a representation of a stabilizer, you can recover representation of this. And in this particular form, it's more useful to think, because here are the two important properties of Robinson, Schoenstatt, Lustig, Bezrukavnikov, Ostrich correspondence, that you can think now of this map pi, that to every element W, it computes A, B, and V, and somehow A, B are defined up to action of GC. And the important thing is that X and Y are left equivalent if and only if pi 1 of X is equal to pi 1 of Y. It's in the same orbit. And because of this, that the inverse will correspond to swapping these two A and B, you can say that X and Y are right equivalent if and only if pi 2 equivalent to pi 2 of Y. The reason I wrote those one of the reasons I wrote the 5 questions that I wrote, let me remind them, is that all these 5 questions can be answered easily using this correspondence. So there are, all of these answers essentially follow from this correspondence. So in particular, 5 would follow if one knows how to compute pi explicitly, and I think at the moment the humankind doesn't know that. So that's why my next question is there an algorithm for computing this correspondence explicitly? And the second question is, it's kind of vague hope. I think in general, for a general Coxeter group, this wouldn't work. That's how we know. But maybe it works for crystallographic ones, because they are Weil groups of Kac-Moody groups. So there is some geometry. There is some Lie theory associated to them. Maybe there is something alone.
Why is it clear that it won't work?
Sorry?
Why is it clear that it won't work? It's impossible?
For general?
Yeah.
Yeah, well, I don't know. You look at something like 2, 3, 11, and you can see that you can't. Well, if you do the ones on the picture, 2, 3, and then start increasing number n, you can see that this small cell has no.
Can you remind what GC and GC connected component are in the classical case?
I'm going to say in a moment. I haven't told you what GC is yet, but I have to get to it. I think my understanding is, I was playing with these hyperbolic ones, but when you put a large, smaller angle, 2, 3, 7, I think this one will have, for large enough n here, this finite cell will have no base set. Okay. Yes, that's a good question. What are these GCs and what are these sets XC? And before I want to give 2 examples and then explain what they are in general. One example is well known in the literature, and so I start with this one. And this will be, let me show it back to the picture. This is this yellow cell in 236. So I have G2, and that's my G2. And the double cell is a double cell with simple reflection, the yellow one in the top picture. In this case, the group is finite, and that's a symmetric group on 3 elements. And the base set, well, there are no alphas here, which means that alpha is trivial. So it's a trivial co-cycle everywhere. Well, anyway, so these groups have no Schur multipliers anyway. So that's a S3 over S3, that's a point, and a 3 orbit. And in particular, using these base sets, you can look at the left cells. So we know that, well, you have to multiply XC with one of these. The number of elements in the left cell you'll get by multiplying XC and computing Euler characteristic. So if you multiply by a point, you are going to get Euler characteristic of XC. What's Euler characteristic? That's a point. S3 has 3 representations. S3 has 3 and C2 has 2. So there are 2 cells of 8 elements. And the last cell, it will be XC times the 3 set. And you can see that you are going to get 3 sets and a regular set of 6 elements. And this one will have Euler characteristic of 2, and this has Euler characteristic of 1. And indeed, if you start counting here, you're going to get 1, 2, 3, 4, 5. This one has 7 elements, this has 8 elements, this has 8 elements. That's a well-known example. Now, less well-known example. Any questions? Now let's go to a less well-known example, which was computed by Paul Gunnels with my help. And this is the cell. In this case, you take W F4 tilde, and well, this is F4 tilde. And the element I'm going to take is S2, S3 squared. So S2, S3 squared. So it's an element of order 2, and I consider it's two-sided cell. And it's interesting because this two-sided cell corresponds to the nilpotent F4A3, which is the only nilpotent element which has a component group S4. That's why it's interesting to compute. And well, in this case, well, we can compute. That's the base set of this cell. So there are 21 singletons. Then there are, so this is 24, this is dihedral group of order 8. So these are 3 sets, elements, these sets of size 3, these sets of size 4, 11 sets of size 4. Then this is Klein-4 group, so these are 6 sets of size 6, and there are 2 Klein-4 groups in S4, 2 non-conjugate ones. So that's this one. The second one is normal, this is not normal. And then there is a single occurrence of a set of 12 elements. This is 1, 2. It's worth mentioning that S3 and C2 have trivial Schur multipliers, but K4, D4, and S4 have non-trivial Schur multipliers. But the cocycles are still trivial. Right? What can I say using this double cell? Well, I would be able to say more if I knew how to compute the correspondence, but obviously we don't. But we can still compute, for instance, size of the double cell. It's 7,408 elements, and the sizes of 42 left cells in this double cell. So you have to multiply, well, just have to, there are 21 cells of size 179, 3 cells of size 193, 11 of 153, 6 of 206, and there is one very small cell of size 151. Questions? Well, anyway. Now, let's move this one to the right. And now, let's go to the representations. Well, Aaron asked the questions what GCs are, so I've showed you 2 examples, but now I'm going to explain what GC is in general. Well, somehow the combinatorics of W doesn't remember this group. You have to do the list theory. So you have to take G. Well, you take a simple algebraic group of the dual type to W. And with, well, the dual type you swap B and C, but otherwise it's the same type. So it's Langlands dual. And you take it over complex numbers. You consider its Lie algebra, and you consider the flag variety of G, which we call B. Then there is this thing called Lustig's bijection. This tells me that there is a bijection between nilpotent orbits in G and double cells in W. This bijection has been, again, discovered by Lustig using parameterization of representations of the Hecke algebra. And then I think Bezrukavnikov proved that this bijection preserves the order and gave somehow geometric description of this bijection. So in particular, let's look at this picture. Back. So here there are 5, 1, 2, 3, 4, 5 double cells. So which orbits do they correspond to? So there is an orbit of a zero element, and the zero element is this one. It's the most non-interesting. The white one is 0. Then there is a principal element. Principal nilpotent corresponds to the red one. Then there is a subregular nilpotent which corresponds to the yellow one. And then there is blue and green, and the two remaining nilpotents is the short root vector and the long root vector. And this one is, I think this one is long, the blue one is long, and the green one is short. Right? Anyway, so I can't draw F4. It would be nice to draw F4, but I can't. Now, Lustig's conjecture. And essentially, well, it's actually two different Lustig's conjectures, but anyway, combined together. But, oh, anyway. So, it somehow up to here, it's proved by Bezrukavnikov and Ostrich. So, all you have to do, now if you want to know all this cell data for a double cell here, you have to pick a nilpotent which corresponds, well, a representative of the nilpotent orbit which corresponds to C. Then GC has to be a reductive part of the centralizer of the nilpotent element. And the finite group is a component group. And in a moment I am going to tell you what XC is. But in the 80s, so in the original version of the conjecture, there was no explicit description of XC, and Bezrukavnikov-Ostrich method of proving it also doesn't compute what XC is. The method is non-constructive. But there is a precise statement what XC should be. And well, essentially XC should be the set of irreducible representations of algebra U chi 0. Let me say it more scientifically, because I'm working over complex numbers. So I'm taking my variety B. I am taking T cotangent bundle. On a cotangent bundle, I am taking coherent sheaves, and I take derived boundary category of coherent sheaves supported as the Springer fiber. And on this category, there is this T structure, which was described by this Rukavnikov, and in this, and you take irreducible representation, irreducible objects in the heart of this T structure. So in a sense, if you reduce everything into characteristic P, well, to an algebraically closed of large characteristic P, then you have a GK and KK, so all these guys will be reductions of this into characteristic P. Then as an extended set, a chi set, you can take well, you can take this algebra. So remember what, let me find my slide before with the definition of a set. So a set was just a G-Marita equivalence class of a finite dimensional semi-simple algebra. So I don't have to use C here. As soon as I use a field of characteristic algebraically closed field of characteristic co-prime to the size of G, I can use any such field K. So what I do, I take reduced enveloping algebra U chi GK. Then I take its block, which at 0 means it's a principal, it's a regular block. It corresponds to 0 Harishchandra character. So this is a block in this finite, in some finite dimensional algebra. Then I can kill a Jacobson radical, and this is a semi-simple algebra. It's a sum of matrix algebras, and AC or A chi, the component group, sits here as a subgroup. So it acts on this algebra. It acts on resolved Jacobson radical. It acts on this semi-simple algebra. And well, so this algebra is a set, extended set. And the conjecture says that this has to be a base set of the cell C. Any questions at this stage? Well, that's essentially two sets, two A chi sets. One which comes from W, one which comes from representations, is are the same. So I have maybe to say what this means. So this algebra, representations of algebra U0 G chi are derived equivalent to this category in characteristic P. And so the heart, this gives me the heart of T structure here in characteristic P, but this, although this object no longer exists in characteristic P, the T structure here exists in characteristic 0. So I can define XC completely in characteristic 0 like this. Okay. Now the last slide, and in the last slide I can try to speculate. Well, I'm going to formulate a conjecture that follows this conjecture, that imply this conjecture. So somehow trying to think how to prove that these two sets are the same. For this, I need all other, well, I need a few bits and pieces. I need asymptotic Yeke algebra, and don't think I have enough time to explain well what it is, but it's some limit of a Hecke algebra when Q goes to infinity. So this procedure in general of taking a limit of an algebra, well, is not a well-defined procedure. It's a bit of a coincidence or luck. It has been discovered by Lustig that you can do that. So you can take this limit, and it's called asymptotic Yeke algebra. And In a sense, it's much simpler. At some point, with taking this limit, I replace this, whatever the scalars there were in my Hecke algebra, I replace it with complex numbers, and Q is replaced with infinity. So J becomes an infinite dimensional vector space over complex numbers with the basis Tx, where X runs over Coxeter group W. The thing about this, that this asymptotic Hecke algebra remembers all the cell structure. So in fact, it splits the fellows Tx sitting in one cell forms two-sided ideals here in this asymptotic Hecke algebra. And left cells form left ideals and right cells form right ideals. Or maybe the other way around, left cells form right, well, it depends how you define it. And essentially, it's a bit mysterious what this algebra is. So, for instance, if some software would be able to compute multiplication of elements in this algebra, that piece of software will be able to compute left cells as well, because this algebra knows everything about left cells. Unfortunately, this limiting procedure is not, well, it's difficult. The second thing I need to explain how it's possible to connect these two objects is Lustig category. It's called MC. It's a category, it's a abelian category attached to a cell. And again, I do not want to describe this category in details. So the full definition requires quite a few technical details, but I'll describe its main properties of this category MC. So it's a subquotient of a, you take, it's a subquotient of the Eva-Hori equivariant Perver sheaves on the fine flag variety of the group G. The second property, important property of this category, is that it's actually semi-simple. So it's a semi-simple abelian category. The next interesting property, that it's a module category over representations of GC. That means there is a bifunctor. Let me just, I have a module category means there is a bifunctor MC rep GC to MC, and the bifunctor satisfies some natural pentagon equation, right? And the last interesting property is that this category MC remembers algebra GC, and it remembers the cell so far. And the way it remembers is you have to take n the functors of MC, which are not just functors but which commutes with this action of the category rep GC. So it's module n the functors. And you take, well, these guys you can compose and you can add them. So you can take a direct sum of two functors. And then there is a K-series, and naturally JC is isomorphic to the K-series of this. And that's what this category, and it's under functors, that's what Bezrukovnikov and Ostrik studied. But anyway, next thing. Duality. Still, somehow, this category MC is quite far from the category of representations of U chi, or from, well, it's just different. And the difference is it's dual. And it's dual in the following sense. There are these dualities for finite dimensional half algebras. And let me formulate it. Let me explain it. So I've switched, now I call my finite group A, not G anymore, because this was A here. And if B is an A algebra, right, then if you take, that's a group algebra BA. And how do you recover your algebra B from the group algebra BA? Well, one way to do it is to use duality. So on this algebra BA, so it's graded by A. So it's a graded algebra over this finite group A. So it has a action, it has coaction of a group algebra, or action of the dual half algebra of the group algebra. So you can take a smash product, and this smash product will be, well, it won't be B, but it will be matrices of size A by A over B. So that's a nice way of recovering an object, Morita equivalent to B, from B star A. So in particular, that's what it means. So B will be Morita equivalent to the matrices, so it will be Morita equivalent to this algebra, and representations of this algebra are the same as graded modules over B star A. Right? So over this Q group algebra. Now here is, I'm going to the main point of my talk, is, well, we have this funny set XC, and we suspect that it appears twice. That it appears, well, that it somehow remembers cells, and on the other hand, it remembers this finite dimensional reduced enveloping algebra. And although we suspect it's the same set, its appearance in these two series is dual. Somehow in reduced enveloping algebras, or in this, inside this category, it appears as, well, via B. But inside this category MC, it appears via B star A. So somehow, to prove that they're equivalent, one has to establish some sort of duality, and that's my final conjecture. That for this AC mixed version of this category MC. What is AC mixed version? So it's, so this is a graded algebra by group A. So it has modules, which like category MC, and it has a graded modules, which is category MC tilde, and there is a functor from MC tilde to MC, which forgets the grading. And I'm not putting many conditions because I'm not, well, because you can put various versions of what has to be satisfied, but there should be some action of the group AC of this category, and there should be a forgetful functor. And also, one needs exact, faithful AC equivariant factor from, well, yeah, that's the conjecture. That there exists this mixed version of a category MC, and there exists a functor from here to here, whose image sits in the heart of a T structure of this category. It's not going to be the same T structure, so it doesn't have to be the same T structure, but it has to sit in some heart of a T structure. Exact means that, well, so this is a semi-simple abelian category, so the image should be, well, that's what exact means, so you go to triangulated category. Faithful means that it should be faithful on morphisms and on objects, so it shouldn't send non-zero objects to zero objects, or should make, well, anyway, so I don't want to go much into detail what this means, but, well, here is my little conjecture. The point of this conjecture is, it looks technical, but this conjecture implies somehow Lustig's conjecture. So if one can have such functor, one can show that, well, that XC, the set of irreducible objects, is the base set of the double cells. And on this bombshell, I want to finish the lecture. Thank you.
Thank you. Are there questions, comments?
So what about the monoidal? So MC is monoidal category.
Yes, it has, but it's. MC is monoidal category. Not sure. Well, this one will be, and the functors will be monoidal category because you can compose them. Right, but MC itself, I don't think. MC squared. Somehow these functors are the same stake in MC squared. And then there will be some convolution.
You mentioned in one phrase at the beginning unequal parameters, and then you never mentioned them again. Is there any hope that something might work there? Or
I don't know much about unequal parameters. I don't know. It looks different even for the ideal groups. Right? It doesn't look. Sorry, don't know. I don't know unequal parameters. I know it's different. Well, no comment. Yes.
That's a sort of a moral question.
Yes.
Why did you want your G equivariant algebra to be same simple? All these, you insist sort of on semi-simplicity, and then on the bottom of the slide, you divide it by a radical. So
Yeah. Well, I don't have
you
to.
insist on semi-simplicity anyhow.
Well, yes. Well, then my definition of a set will be different. Then you have to take a reducible set. Well, yeah. Yes. Because you essentially taking only irreducible, morally you're taking only a set of irreducible modules. And the irreducible modules, the radical is killed on all of them. So you can just kill it off. So, so two algebras, you have two algebras which are not semi-simple. And then you can, this has the same group G which acts on them. And they can still have the same irreducible sets. That means somehow they're quotient by radical Morita equivalent. For example, this full algebra will have the same set of irreducible modules as the quotient algebra. So somehow a Morita equivalence class of non-semi-simple algebra is not a set, but a Morita equivalence class of a semi-simple algebra is a set.
further questions? Let's thank the speaker again.